Nowadays, we take warm and comfortable houses for granted. 90% of houses in the UK have some form of central heating. Nearly 3/4 of these are fuelled by natural gas. 100 years ago, things were very different. Most houses were heated by coal, and in 1900, nearly 1 million men worked in mining, a dirty, dangerous and poorly regulated private industry. Coal fires were inefficient and chimneys belched out numerous pollutants, the most visible being soot, which blackened buildings and caused smog. Unlike in modern houses, chimneys were a necessary part of the design because fireplaces were provided in nearly every room. Each fireplace was served by a separate flue, and several flues could be contained or gathered into a single chimney stack. Hot water would have been heated on a range or in a separate coal-fired boiler. Soot from chimneys continued to blacken buildings and threaten health until the Clean Air Acts of the 1950s. By the 1850s, most cities had their own gasworks. Gas was made by heating coal in iron tanks and then distributed in underground cast iron pipes. To meet fluctuations in demand and to maintain pressure over distances, it was stored in telescopic gas holders which rose and fell according to the amount of gas in them. Until the 1900s, gas was mostly used for lighting, but rarely for heating, partly because coal was still cheaper, and partly because effective gas fires required clay radiance. These were not perfected until the 1920s, by which time gas was no dearer than coal. A typical new house in the early 1930s might still have a coal-fired range in the kitchen or living room. The sitting room and larger bedrooms often had traditional coal fires set in decorative tiled fireplaces. But modern gas fires were becoming increasingly popular. Gas fires could be switched on and off in an instant, and the heat was easy to control. Gas cookers with effective oven thermostats were also appearing on the market and quickly replaced coal-fired ranges where cooking temperatures could be very uneven. Gas could also be used for heating water as and when required. A single geyser could be located above the sink, or a multi-point geyser could be located anywhere, serving several taps.
Happy in the morning, 'cause the water's hot. We can bath an army, the ascot does the lot. Happy after breakfast, 'cause the water's hot. Dirty, greasy dishes are left without a blot. Cleaning house has no more fears, the ascot's waiting there. Saving money, sighs and tears, and endless wear and tear. Happy in the evening, 'cause we know we've got water, water everywhere, and always boiling hot.
By the 1930s, electrical lighting was now standard in new housing. Many older ones were being upgraded. Electric fires soon followed. Their advantage over gas was safety, portability, and they didn't need a flue. Electricity could also be used to heat water. The appliance manufacturers recognised the potential of advertising and promised a revolution for the housewife.
Now, Mrs. Smith, here's a neat fitting. Keeps 10 gallons of water scalding hot. That ought to be sufficient for your household, I should say. Even if Mr. Smith has a tub every night and you have one every morning, there should still be plenty of water to wash up the dirty plates and do all the household jobs which will require hot water during the day.
Well, I never.
Well, I never.
Early hot water cylinders were usually made from galvanized steel. They could be located anywhere in the house, not just over the bath. In most 1930s houses, they would have been in an airing cupboard. The water in the cylinder was heated through an electric element called an immersion heater. Galvanized cylinders were heavy, expensive, and prone to corrosion. By the early 1930s, improved processing of low-grade ores made copper a viable alternative. Copper cylinders quickly replaced steel ones because, cost apart, copper has a number of advantages. It's strong, light, and easy to handle. It's easy to shape and easy to join. In hot water systems, it's ideal because it's long-lasting, corrosion-resisting, and helps inhibit the growth of many microorganisms. Early hot water cylinders could not be fed directly from the mains. As the water was heated, so it would expand, forcing warm water down the incoming main, or even splitting the cylinder. To get round this problem, the cylinder is fed from a storage tank, usually in the roof. As the water in the cylinder heats and expands, the level in the tank rises. If the immersion heater goes wrong and the water boils, it can discharge through the vent pipe into the tank and out through the overflow. The water could also be heated away from the cylinder in a boiler, often situated behind the fire. An early back boiler was basically a cast iron tank heated by the flames. The hot water would slowly rise to the cylinder through copper or lead pipes. The cooler water from the base of the cylinder would return to the boiler to be reheated. As hot water is drawn through the taps, fresh water is fed to the bottom of the cylinder from the tank in the roof. This water then slowly circulates through the boiler and back to the top of the cylinder. This means that the water coming out of the taps has been heated directly by the back boiler. It could sometimes be tainted with particles of rust inside the boiler. More serious was the risk of limescale deposits. These occurred in hard water areas and led to furring of the pipes, reduced flows and even blockage. Furring was worst where the pipe was hottest. These problems were resolved by passing the hot water from the boiler through a coil within the cylinder. This keeps the water in the boiler circuit separate from the tap water. This is called an indirect cylinder. The water which heats the cylinder flows from the boiler through the cylinder coil and back to the boiler. Other than when it leaks or is drained down, this same volume of water just goes round and round and round. The risk of limescale is minimised because the water is not constantly replaced. This circuit requires its own feed and expansion tank, separate from the tank which feeds the cylinder. This avoids the risk of any contaminated water coming out of the taps. Add an extra loop of pipework and connect a heated towel rail or a couple of radiators, and you've got the beginnings of a modern central heating system. During the 1950s and 60s, electric heating was popular in flats. It was cheap, easy to install, didn't require a flue, and unlike gas, there was no risk of explosion. Underfloor heating was common and usually comprised a series of copper wires within the floor carrying electric current. An insulated ceiling prevented heat loss into the flat below. It was not very successful. The floor was heated at night using cheap electricity and steadily lost its heat throughout the day. By the evening, when the heat was most required, the floor could be quite cool. All-electric heating was also popular for low-rise housing, usually in the form of storage radiators. In fact, by the 1960s, few houses were being built with chimneys. Electricity from coal-burning power stations was cheap. A typical storage radiator contained 4 metal elements which at night heated high-density blocks. The stored heat was slowly released during the day. The amount of heat stored, and to some extent the amount released, could be controlled, but not very effectively. In the 1970s, back boilers were still common, but often gas-fired rather than solid fuel. The boiler, situated behind the fire, heated the hot water in the cylinder and could also heat radiators. In this example, hot water from the back boiler circulates through a coil in the cylinder located in the upstairs airing cupboard. This is therefore an indirect cylinder. A vent pipe continues into the roof space to allow the water to escape into the feed and expansion tank in case the boiler overheats or even boils. The larger feed and expansion tank supplies water to the cylinder, the water which actually comes out of the hot tap. When the tap is turned on, the weight of water in this tank forces water through the cylinder and out of the taps. The higher the tank above the taps, the better the pressure. The tank is refilled from the mains through the float-operated valve. In most cylinders, an electric immersion heater allows the water to be heated without using the boiler. If the water in the cylinder overheats for any reason, it can vent back into the feed tank. Back boilers are still made today. The fire, which can be switched on separately from the boiler, provides a focal point to the room and a local controllable heat source. Nowadays, more than 90% of houses have some form of central heating. A relatively small percentage of these are modern storage radiators and underfloor systems. The vast majority of them are water-based boiler and radiator systems, fueled by natural gas, oil, propane or solid fuel. Natural gas is relatively cheap and has low CO2 emissions. Large reserves were discovered in the North Sea in the 1960s, and it slowly replaced the much dirtier coal-based town gas. In a typical domestic system, water is heated in a boiler and then distributed to the radiators through a network of pipes, nearly always made from copper. Copper is an ideal material for pipework. It's light to handle, easy to cut and shape, easy to join, and very durable.
Right, to solder a fitting you need to put flux onto the pipe, very small amount. And then we're ready to solder.
These fittings are known as end feed fittings. Solder is drawn into the joint through capillary action, forming a neat, reliable joint. End feed fittings are light, making handling and installation easy. In addition, the fitting's smooth lines are unobtrusive on exposed pipework. These fittings contain a ring of lead-free solder. When heated, the solder is released, forming the joint, without the need for additional solder.
Before you solder, you need a small amount of flux on the pipe. As you're heating, you keep heating until you see a slight amount of solder just coming from the end of the fitting. This is a compression fitting. You have a nut and an olive with these. Put the nut on first, followed by the olive.
Compression fittings don't require solder. Tightening the coupling nut squeezes the compression ring onto the tube to form a strong joint. Compression fittings are ideal for use where it would be damaging or dangerous to use a naked flame, or where the joint may need to be broken and remade in the future. They can also be used on wet pipes. Copper tube manufacture begins with the refined sheets known as cathodes imported from Asia and South America. The cathodes are melted in a furnace to a temperature of 1100 degrees Celsius. In this furnace, about 15 tons per hour are produced. The copper is cast into a continuous solid cylindrical shape, which is cut into short sections or billets. The billets are then heated in another furnace to 950 degrees and are now ready to be extruded. This is done through a die, and it forms a long seamless tube known as a shell. This shell now needs to be reduced in diameter, and this is done by controlled stretching, a process known as cold drawing. It's important during this process that the copper has the correct purity, at least 99.97%, otherwise it would snap during the drawing process. As the tube's diameter reduces, the copper hardens and loses its malleability and therefore its workability. This is restored by reheating, a process known as annealing. In a typical year, this factory produces enough copper tube to go round the world twice. In a typical modern central heating system, a gas or oil-fired boiler heats the water. This circulates through an indirect cylinder and through the radiators. A vented boiler, sometimes called a traditional boiler, will be fed by a small feed and expansion tank, usually in the roof space. At the heart of most traditional boilers is a cast iron heat exchanger. This is heated by the flames from the burner and in turn transfers its heat to the water flowing through it. The fins in the exchanger provide a large surface area to extract as much heat as possible from the flames. A burner, in this case gas-fired, is fixed below the heat exchanger. An electric fan brings in air for combustion and expels exhaust gases. If the fan fails, the boiler switches off automatically. The boiler is managed by a circuit board mounted in the bottom of the casing. A boiler heats the house by pumping hot water through a series of heat emitters, commonly known as radiators. The amount of heat that the radiators emit depends on their size, as well as on the temperature of the water. The surface area of a radiator can be increased by making a single radiator larger or by using two panels back to back. As the water flows through each radiator, heat is drawn from it, so the water which re-enters the flow pipe gets progressively cooler. This may be okay for very short runs, say in a small flat, but not for a typical house where 10 or more radiators may be served. A two-pipe system overcomes the problem. Hot water is delivered to each radiator straight from the boiler. The cooler water, leaving each radiator, is returned to the boiler through a separate pipe. Valves either side of a radiator allow it to be removed and can also control its heat output by restricting the flow of hot water. Thermostatic valves will automatically respond to room temperature.
This is a thermostatic radiator valve. This controls a single radiator, and it works by having a wax sensor inside the head, and that expands as it gets warmer. It will then push down onto a pin which closes the seating of this valve, therefore shutting off the radiator. When you adjust it, all you do is you move the head further down or further up to make the distance of travel increase. One thing this does is control the radiator locally, but it cannot switch the boiler on or off.
Old systems relied on gravity to circulate the water. Nowadays, systems are always pumped. The pump can be separate or an integral part of the boiler. The water for the radiators and the cylinder are on separate circuits. A three-port motorised valve allows these circuits to be controlled independently. A ball directs the water from the boiler to the cylinder, to the radiators, or to both. Most modern systems include a bypass valve, in some cases within the boiler. If all the radiators are closed down by thermostatic valves, water can still flow through the boiler without flowing round the whole house. It also maintains pump pressure and reduces noise. Add the pipework which provides hot water to the taps, and you almost have a complete modern vented heating system. All that's missing are the various electronic controls to switch it on and off and regulate the temperature. Three key switches are the programmer, the room thermostat, and the cylinder thermostat.
This is a programmer. All this is a timed switch. You have one switch for hot water, one switch for heating. You simply set the controls to say when you want to be warm, and then this will automatically switch power through to the thermostat in the on periods. This is a room thermostat. This is just a temperature operated switch. When power comes through from the programmer, this will allow power to go through to the motorised valve until the room is satisfied. When the temperature in the room is warm enough, this will switch that power off and prevent the boiler from firing. This is the cylinder thermostat that does the similar job when fitted on the side of the cylinder. So you can now control the heating by time and temperature, the hot water by time and temperature independently. This is the motorised valve. It's the key to the system and it joins all the other controls together. Very simply, this governs where the water is going to go around the system. It comes up from the boiler and goes to either the heating or the hot water. The position of the ball inside that governs that flow is determined by the timer and the thermostats. If the programmer and the thermostat for the room temperature are calling, then the valve head moves to one position and the pump and the boiler fire. If the programmer and the cylinder thermostat are calling, the valve moves back to another position and again the pump and boiler fire. But more importantly, when both heating and hot water are satisfied, the boiler is switched off.
A conventional vented system requires 2 feed and expansion tanks. In a block of flats, there could be dozens of tanks in the roof space. This can be noisy, heavy, and there's a high chance of leakage. An alternative method is to install the tanks within each flat. One way is to use a special cylinder with the feed and expansion tanks above the hot water storage. This reduces the amount of pipework, but as far as pressure at the taps is concerned, delivers a much slower flow. They will not provide enough pressure for a shower, for example. Another way of getting rid of the tanks in the roof space is to use a sealed system. The boiler is filled directly from the mains, and expansion of the hot water is accommodated within a pressurised vessel. The hot water cylinder can also be mains fed and has its own pressure vessel to accommodate water expansion. In these sealed systems, there are low pressure safety switches and high pressure release valves to prevent scalding or explosion. A different approach, originally designed for flats but nowadays used in houses as well, is to install a combination boiler. There are no tanks and no cylinder. Hot water for washing is heated direct from the mains as and when required. These are more sophisticated than conventional boilers and slightly more expensive, but they are easier to install as less pipework is required. Nowadays, almost half of all new heating systems use combination boilers.
The difference between a conventional boiler and a combination boiler is that the combination boiler doesn't require a hot water cylinder. It will heat the hot water up instantaneously through the boiler itself. At the top we have the fan, pulling in the combustion air and also sending out the flue emissions. We can see the gas to water heat exchanger. That's where our primary water is going to be heated up. This is our main burner, where you will see the flame through the spy hole. The gas valve, expansion vessel at the rear, and that is to cater for the expansion of the central heating water, because this boiler will be going on a sealed system. It's going to be a pump system, so there's our pump at the front. And down the bottom here, we have a water-to-water heat exchanger, or some people call it a plated heat exchanger. That's going to contain compartments of tap water as well as primary water. So we'll be heating up primary water and passing that heat on to our domestic tap water. The combination boiler from the onset will be a more expensive boiler to buy than the conventional boiler. However, you're cutting down on a lot of pipe work, a lot of labour, and of course there's no cylinder required, so you are making savings as well.
In a modern oil or gas-fired boiler, about 70 to 80% of the fuel is converted into useful heat. The remainder is lost through the flue. The flue gases can be as hot as 250 degrees Celsius. In condensing boilers, more heat is extracted from the fuel. Their efficiency can exceed 90%. In fact, so much heat is extracted that the flue gases are only about 50 to 60 degrees. In a typical condensing boiler, there are two heat exchangers. After crossing the first one, the combustion gases are directed over the second heat exchanger to preheat the water returning from the radiators. If the water in the radiator return pipe is cool enough, the gases will condense, releasing all their latent heat. The secondary heat exchanger must therefore be corrosion resistant, and a drain pipe must be fitted to remove the condensate. Because the exhaust gases are so cool, they mist or plume. This is quite normal and proves the boiler is working properly.